Okay, so today's lecture we'll be going through probability distributions and sampling. Okay. By the way, I'm just in this course, I'm just giving you a brief summary of these. Each of them require a full-fledged course. Statistics. We have taken statistics and best, right? This is a small part of it. Okay, before we go on to the main topic, let us recap what we have done previously. Okay, so what standard deviation tells us about the data? The deviation from the mean. Okay, what are outliers? Outside what? Outside the pattern. Okay, good. Okay, what are the principles of data visualization? There. Data visualization. Here, match the data equals accuracy. Okay. Anything else? Okay. Should be clean, right? Clean and clear. Okay. Good enough. Let us move on. So when we are dealing with data, we have a population of data and we have a sample of data. Okay. Population means your entire group of interest. Okay. So if I'm focusing on a concrete sample of a type, then all possible concrete samples of that type are my population. Okay, if I am talking about a highway, okay, then all traffic on this highway from start to end is my group of interest. Okay, that will be my population. Okay, so the example is given here, which I already mentioned, and then we have a sample, which is a subset of the population, a part of the population. Okay, so from all the concrete possible concrete samples you can have, you select a number. Okay, you select the number and that will be your sample. Okay, and then on that sample, or from that sample, we calculate inferential statistics. Okay, inferential statistics means that use the sample data to make conclusions, results about the population. Okay, so inference basically means that you are looking at something and trying to guess the bigger picture. This is inference. Okay, so for example, I was giving this example for something else today. Like we had a teacher, and he was very strict. He is some I don't know, for example. So he's very strict. So some of us we took classes with him in our bachelors. Then we came to masters, and he was from a different field. So you are not supposed to see him in the masters. Okay, like we were not supposed to see him. Now you see. Okay. So something happened, and for a course he came. Okay, and there was a friend who did not attend like 2 or 3 lectures at the start. He was like you guys are working. He was working and he was somewhere else. So in one of the lectures he came and he saw him for the first time. He didn't know that he's teaching. He sat there for one class and he came out and he said, I am going to get an F. Okay. I cannot do it. So this is what inference. From one lecture, he made a conclusion about his grade. Okay, at the end of the semester. So this is like sort of an inference. Okay. So inference is you look at something which is small, apart, and you try to make a claim or a result about the whole thing. Okay, the bigger picture. And we, obviously, to take the whole population is extremely difficult. Almost impossible. Even the governments, okay, they don't take the data of whole population when they are doing the data collection basically. Okay. But now, we have certain things which are collecting the data continuously. Okay, right? Yeah. So they are continuously collecting the data. Only thing, maybe then you go out of the range, the signals are dropped, phone switches off. Otherwise, they are continuously collecting the data. Okay, but again, you cannot use the entire data set, even in that case. You may say, no, I have the full data, but you don't. You don't have. Okay. So even in those cases, we focus on a sample. Okay. In some cases, the entire data is not possible. For example, concrete. You cannot test all possible samples of every type of concrete. It's not possible. Okay. And all different combinations of factors. Water cement ratio, size of aggregate. It's not possible. In cases where it is possible, or in cases where we can see the data in front of us, but we cannot, it's all not usable. So, I gave the example of the phone data, or uh, they collect the traffic data. For example, they have traffic sensors, they are installed on the roads. They are continuously collecting the traffic data. But still, it cannot be for the entire domain. Okay. And even those sensors, they have their own errors. Okay. So even the data which is collected 24/7, you cannot use it. That data itself is not the whole population, and even if you get it, you cannot use it. Okay. So we had that data for, I don't know, 500,000 samples for traffic accidents. It was not 500,000, it was 240,000 something. And then we did some simulation with the data, it reached up to 500,000. Okay. But to process the data, it takes like a very large amount of time. Okay, with the machine. So this takes like 10 seconds to come on the projector. Can imagine what will happen to this machine if it is running 500,000 samples. But this has happened. Okay. So in any case, the point is the data of the entire population is never used. Okay, it's never used. So and the examples, even if you are talking about one pipeline, you cannot analyze, or you cannot take observation for each and every micrometer of that pipeline. You have to still do the sample. Okay. So when you are collecting the data and we are working with the samples, we assume a normal distribution, which is also called as Gaussian distribution. Okay, and it is characterized by a bell-shaped curve. Okay, so this is a bell-shaped curve because it looks like a bell. Okay, and there are three things about this bell-shaped curve. Two of them are written here. One of them is written there. The two things are, they are symmetric, bell-shaped curve, symmetric and unimodal. Okay, symmetric means what? Huh? Yeah, same on both sides, which also means this. Okay, or this. This is symmetric. The mean is exactly in the middle. Mean is the middle value. The mean is exactly in the middle. By the way, it can the mean can go here and there. Okay, and I will show you. Okay. See this one? This is the median. This is the mean. close, close. See this one. Mean is outside. It's in the upper duplex. There's still under the outlier, but you see the whole box. It's outside the box. Okay. And this is mainly because of maybe one or two values. Yeah, like maybe 10, 15 values. One or two values is very high. Okay. So, and this will bring us to another point, which I will show you later. Okay. But this can happen. Okay. Even in this case, you see, this is the mean. And your median is there. It looks in the center, it's not, because the median is there. Okay.
Because most of the data
Yeah. Yeah. But even in some cases, most of the data is not there.
is still there.
There's still that one value which is quite big can have a lot of impact. Yeah, anomaly. So the size of the anomaly is also another point. It's not about having an anomaly. Okay, obviously, if there are too many anomalies in your data is already there. So there are too many which are here. So that it seems like the mean is within the data. But the mean, the data itself is on the higher side. So there are too many values on the higher side. Okay, but in this case, this is not because of the anomaly itself. It is because of the size of the anomaly. This one value has taken your mean and shifted it so much up. Okay. So dealing with the inferential statistics, this can happen. Okay. So we were saying it is symmetric. Okay, which basically means the mean and median are almost the same. And the third thing is it is unimodal. Okay, unimodal means what? Basically, one peak. Okay, one peak. And since it is symmetric, so that one peak will be where? In the center. Okay. The third thing, which is not written here but written here, is asymptotic. Okay, asymptotic means that the extreme values in the data have less possibility. Okay, the medium range of the data has higher possibility. So in other words, the data is centered, or the number of values are majority is the center. This is what asymptotic means. If you go away from the center, the number of values, the percentage of values go down. Got it? So this is these are the three conditions of a normal distribution. In other words, of a Gaussian distribution. Okay. So this type of distribution is defined by two parameters. Okay, one is called the mean, the other one is called the standard deviation. Okay, mean tells you about the center of the data. Standard deviation tells you about how far from the center you have been. Okay. If I give you these two things, you can plot this data. I give you mean and standard deviation. You can plot this thing. We have equations for that. So you go and search for normal distribution equation, find the equation. Okay. And that equation you will use mean and standard deviation. Okay. But if you just have a look at it, if I know how much is this value, if I know how far I have to go standard deviation, I can make some sort of a plot, right? Okay. If I don't use the equation, it will not be that accurate, but it will look something like this. Okay. I not need many things here. There is an empirical rule which can be applied on this type of distribution. That empirical rule is called as central limit theorem. Okay. Central limit theorem, I mentioned about asymptotic, right? Asymptotic means what? Yeah. Okay. So this is what the central limit theorem is saying. It's saying that if you take one standard deviation equal to space in the center of the data, you will cover 68% of the data. Okay. If you take the central width of the data up to 1 time the standard deviation. So this is your mean, right? So you do 1 time standard deviation here, 1 time standard deviation here. This will cover 68% of the mean. Okay. So 68% is a lot, right? 2/3, more than 2/3. Okay. If you go up to 2 times the standard deviation, you will cover 95%. And if you go 3 times standard deviation, you will cover 99.7%. But you can also see another thing, which again related to being asymptotic, is as you are increasing your interval, the number of values which you are increasing is not so much. So 1 standard deviation, 1 standard deviation. How many you covered? 2/3 of the data. If I increase an interval by 1 standard deviation more on both sides, how much data I'm adding? Less than 30%. Okay. So up to 1 standard deviation covers 2/3 of the data. Up to 2 standard deviation, I not even reach 100%. Okay. So as you are getting far from the center, the number of values which you will cover is very, very less. Okay. And then if you increase even 1 more standard deviation, how much you are covering? 4% something. Okay. So again, going back to the asymptotic rule, as you keep on going away from the center, the number of values which you will incorporate in the data are getting less and less. Okay. So this also brings us to the concept of outliers. Why we don't want them? Okay.
They will come to shape.
Huh?
Function.
They will
They will affect the shape.
not only maybe they are in the shape. Okay, maybe they are following the shape, but they are far from the center. Like the box plot I showed you. Yeah, like the box plot I showed you. Okay, so if I go after those outliers, okay, if I adjust my values because of those outliers, the number of values which I will add to my observations will be very few, but it will destroy everything. It will destroy my mean, it will destroy my median, destroy the whole distribution, the whole shape as well. Okay, so you will ruin a lot of things because of a very small percentage of values. The 95% is because somebody saw it in a dream.
What's me?
We say 95%, yes. That's true. Okay. But why? Okay. So now why we are discussing this distribution? Because it has been argued and it has been found that many natural phenomena and measurements, they follow normal distribution. Okay. Many natural phenomena and measurements, if you are taking them naturally, even if you are just in the lab, it's about something which, you know, you made a concrete sample which is made up of natural materials, right? Okay, so something like this. So when you look at that thing or the measurements of that thing, it should follow a normal distribution curve, a Gaussian distribution curve. Okay, and it is mainly because of the errors or variation. Okay, so if I take all the error from the observation out, you will always get the perfect value. And there can be only one perfect value, not many. So if you take 3 concrete samples, which have the same components, the same ratios, okay, should you get the same value?
Yes.
You should, right? But we don't.
Because conditions are not ideal.
So there are some errors. It's not like in terms of it's something negative. Error is anything which is causing the variation.
Yeah.
Okay. So if all these things are taken out, the only thing which you will be left with is one perfect value, and that value will repeat. Okay. So the thing which is causing the difference in the values is the error, the changes in conditions or whatever. Okay. So the what we are saying here is not the values follow normal distribution, but the errors, the variations in the values follow normal distribution. Okay, and where have you heard about this? The error theory. Huh? Huh? Chemistry lab, yes. It would be yes. Statistics, yes. Okay. Any other rules? Huh? Numerical, you did? You do? Okay. Already. I thought numerical was like theorem center. We do this as well.
Yeah, we do that.
We do statistics as well. Numerical. Okay. But
It's it's rational and powerful statistics.
okay. But I was referring to survey. Surveying they have the whole theory of errors. When we are making these courses, Pradal was saying we don't want these courses to be like you have to add a few course about theory of errors.
There's no one's error.
Huh?
There's no one's error.
And he was there was a big debate like what courses we have, the core courses. Okay, and this was in the old days because you have seen the old plan, the plan in which we were taking the admission. This course was not announced. Okay, that was not announced. Okay, so those courses where they have project management and finite element, he was basically not AI, he was arguing about finite element.
Still have finance.
Yeah, you guys have this. Go ahead, no problem. But why everybody has to,
Yeah, for structure.
yes. This was the point. If you want something numerical, because the point was finite element means that we are teaching you how to do the modeling and so on. He said instead of finite element, theory of errors. It will give you a better chance of modeling. Okay, and a fun whole semester will be done. So, going back to the point, they say that natural phenomena and measurements, they follow normal or Gaussian distribution. Obviously, they are saying the values follow the normal or Gaussian distribution, but in the background, the values are affected by the errors. So the theorem or this claim is mainly about the errors, because if you take out the errors, you will be left with one value. So the Gaussian distribution is because the errors follow the normal distribution, the Gaussian distribution, not the value itself. Value should be what? Perfect, one value. When you take an observation, there should be one perfect value. Okay, but the errors or the variation will not let it happen. Alright. Okay, and this is the difference between the normal range and then the outliers. Okay, the outlier is not because of the error. Outlier is because of something has drastically changed. Conditions are not the same now. Okay. Okay, so once you establish this fact that the data is following normal distribution, then it opens up a lot of analysis for you. Okay, for example, you can do the t-tests, you can do the ANOVA analysis of variance. Okay, you do that in numerical. These tests, ANOVA t-test, do you do that in numerical? No. Okay. But ANOVA is very similar to regression. ANOVA is very similar to regression. ANOVA is the analysis of variance. Analysis of variance. Variance, ANOVA. and t-test is t-test. Okay. T-test is what we did in the traffic or speeds. Okay. But the point is, as I said, all this requires another whole course. Okay. And there's a course only for these things. The PhD, take admission for PhD. I don't know why you do that, but if you do that, you will have a whole course which is about statistics and probability. So the point is, having normal distribution or knowing that data follows normal distribution opens up a lot of analysis for you. Okay, and on the basis of those analysis, I can make a lot of inferences about the data. So otherwise, I give you a sample and tell me something about this particular item from this sample. So if you do not know that the data follows normal distribution, cannot make your claims about the item itself. So I give you 30 data of 30 complete samples. I tell you, okay, if I use the same mixed design, what mean should I expect? How much variation should I expect? Okay. So you can only tell me if you have an idea about the distribution of the data itself. So this assumption or this claim that data follows normal distribution opens up that I can perform those analysis which you normally do. Okay. Otherwise, mean and standard deviation and these things do not matter. Okay. Like you were talking about 95%, right? 95% confidence level. Now it is so commonly used that nobody even asks why 95%. Nobody. Okay. They said, okay, what was the confidence level? What was the percentage you took? And we say 95%. They say, okay. Done. Nobody asks why 95%, why not 99%, why not 90%? Okay, fine. So 95% is the result you got. Done. Same thing with the other things which you normally use. Use mean, right? Okay. And you calculate mean with a specific equation. You use standard deviation. And you calculate standard deviation using a specific equation. Okay. So those everything which is considered normal in statistics comes from normal distribution. That's how you got normal. Okay. So the point is that making the claim that the data follows normal distribution opens up a lot of analysis which are on the basis of this claim, and then those analysis help you to make claims about the data or to know about the data. Okay, I already mentioned about central limit theorem. Okay, and yeah, the main central limit theorem, those things, these are rules. These are rules under central limit theorem. The main theorem is this one. The sampling distribution of the mean will approach normality as the sample size increases. Okay. So you are more close to having this bell-shaped distribution. Okay. If your number of samples are increasing. Okay. The number of samples are increasing. And even if the data is not originally normal. Okay. So if you look at one sample of the data, it may not make this normal distribution. But if you keep on repeatedly taking samples after samples from the same population, okay, then it will start to look more like a normal distribution. Okay, this is the whole idea behind central limit theorem, and that will allow us to assume normal distribution and then make inferences about the data. Okay, just one thing here. When we say samples, okay, the samples used in the central limit theorem, each sample is a set of values. Okay, not a value. Each sample is a set of values. So central limit theorem says if you take samples enough times, number of set of values, number of set of samples. Okay, because you took sample now, This is one sample. Okay, now I'm saying if you take enough samples of number of samples, then the data will start to look like normal distribution. Okay, and the inferences which we are making about this, the rules which we are applying, they are basically giving you not the range of data. They are giving you a range of expected value of the data, which we normally say mean. Okay, so according to statistics and according to probability distribution, the expected value of the data is called as mean, not the summation of value of a number. They don't mean. This is averages. Okay, so central limit theorem applies to set of values, not the number of values in each sample. Okay, obviously, if you keep on increasing the number of values, then even in one sample, you start to see the shape. Okay, but the idea is that the central limit theorem is applied to a number of samples or a number of set of samples. Okay, and the rules it is giving you is not about the data itself. It is about the expected value of the data. Okay, so this is not the range of data. This is a range of mean you can get from those samples. Okay, so for example, you take 30 samples, you have one mean, right? And you take those 30 samples 100 times. Okay, so now you have 100 sets of values. And you have 100 means, right? For each set of mean. So central limit theorem tells you that for those 100 sets, the mean 68% time is in this range, the mean. Out of those 100, 68 of them will have mean in this range. Okay. And because if you calculate, for example, if you have a data set, you calculate this range for that data set, you get a very small interval. Okay. So maybe your data, like we did it traffic and nobody asks at that time. Okay, then your data is going in this. If you know, it's the same example I will use, same big example from the book. Okay, so the lowest value is 30 to 34, something like this. The highest value is 68, something like this. 34 to 68. Okay, and when we calculate this range for that data set, it's one sample, right? The example we are using one sample. When I calculate the range is between 40 something to 50 something. Okay. Nobody asks me that you are saying it is 95% of the data, and your data is going from 30 to 60 something, and now you are showing 95% of data is there. It's not there in this sample. Anybody can see it. Means 40 something. It's not a big range. It's not like 41 to 50. It's not like this. It's 48 point something to 51 point something. So it's like 2-3 miles hour range. 2-3 miles per hour range. So there's no way 95% of that sample is in this range.
Unless that's. And only maybe only one. Yes, really.
But the point is that confidence interval is not supposed to give you 95% of that sample. It is supposed to give you 95% of the means of the entire population you can expect. Okay, because if it was giving you the 95% of data, then the range would be very high. It's not giving you the 95% of the data itself. It is giving you the 95% of means of the data.
So it's.
That's why it's interesting. Yeah, but not the whole population. And means of the population, expected value of the population. Okay, so like I said, I'm telling we have taken traffic, right? Now she cannot stop talking. There she did not ask, right? Why is it 95%? Our data has a range of 34 miles per hour, and we are saying 95% is 3 miles per hour. Nobody asked, right? Okay. Because I'm so good. So good in cheating. But earlier when I came here, I used to tell these things. Okay, because back in Pakistan, I used to teach probability statistics and so on. So it was all fraction in my mind. Okay. So I used to teach them that see they are talking about not the mean, they are not talking about the population or the sample, they are talking about the mean of the population and so on and so forth. And but then I get to know Bucharest. And then I'm wasting my name. Since even if I say this is for the whole population, you will believe me. Why should I bother? Okay. But anyway, you are at the higher level, you should understand these things. That we are not talking about applying the central limit theorem to the population itself, but the mean of the population. Okay. So an example here, for example, if you take the strength of one concrete sample, it can be any value which can go from very low value to very high. One sample can go anywhere. Okay, but the average of 30, okay, is more normal. It's more, as they say, more predictable. Okay, and the same thing, for example, if I take the student grades, grade of any particular one student can we go from A to F. Okay, but an average I know is normally around B. Most of the courses. Right? I think there are those courses. But it's not it's the case, right? Okay. The same thing with the average travel time. If I tell you what will be your travel time today, okay, that one value can be 5 minutes to 50 minutes. But if I ask you what is your normal travel time to go from here to your office, you'll give me a value which is very normal. Because we have taken many samples. We're not talking about one day, we're talking about many samples. So it becomes more predictable, more normal. Okay, inferences become easier. Okay. So let us try to visualize this empirical rule. Okay, if we simulate 1,000 values from a normal distribution, meaning that the mean is 40, so there is no data required. You are generating your own data. This code will generate a distribution itself. Okay, and it will plot the histogram as well. So as I said, for normal distribution, if you want to generate any normal distribution, the things which you need is mean as standard deviation. Okay, the mean of 40, standard deviation of 5. If you want, you can change it, no problem. Okay, so this is like the comment what we are doing. This will generate the code. Oh, sorry, this will generate the data and store it here. This is what I was telling you about earlier. If you don't do this, this will still work. It will not save anything. Okay, yeah. So this will be saved here because of this. You have to do this if you want to save anything. Okay. So this is to create the distribution. Okay. And then this is to plot the histogram. Obviously, these are the label on the x-axis, the mean label of the chart, and so on and so forth. Okay. This command will make sure that the histogram is about probability. Okay, it's about not. It will calculate probability histogram. Yeah, right. Very good. Okay, so this is like the random normal, and this is like the normal distribution itself. Okay, like the best fit curve. This is like the best fit curve. This is the histogram which you see is for your values, which are randomly generated. Okay, and then this command will make a best fit curve fitting your histogram. Best fit curve. All right. Okay, and you can calculate the mean now. What should be the mean? The one which you gave, right? You can cross check it now. Are you getting the same mean as standard deviation? Okay, you can generate it yourself, and you can also find out the. It's just to check.
Yeah.
That's okay. Obviously, you should be getting the same one. Yeah, and this will give you the percentage of values within your data. Okay, what percentage? They are doing 1 plus minus 1%. What percentage will get? How much? 68%. Okay, and if you do 2 times, then 95, right? Okay. Which is statement. What? You say that this statement is safe, right? This is a comment, doesn't go anywhere.
So, complexity to that, we can.
Okay. So you can calculate any interval from your data using this statement. You can change these values, calculate the percentage. It will give you the percentage of data. Okay, so this can be very helpful. You can see it. You will later on use it as well. And some of the exercises later on. I have it. I can give it to you. But in some cases in your research, for example, you know how state of the art lab technologies we have in UOB, right? How good our lab are. Test anything, right?
Yeah.
Okay. So in some cases, you may use this methodology to create your own data, simulate your own data. Okay, this can be done. Okay, so the parameters which you calculate for a sample are called as sample statistics. Okay, so for example, mean is a sample statistic, standard deviation is a sample statistic. This range is a sample statistic. Okay, so the sampling distribution, okay, tells you about the distribution of a particular statistic calculated from all possible samples of the population. Okay, so if you take samples for the entire population, if you have enough samples which covers the entire population, okay, then sampling distribution tells you that what will be the distribution of that statistic in the population. Okay, the thing which I mentioned earlier, okay, about the central limit theorem. As n increases, the sampling distribution of the mean becomes normal. Okay, so it will start to look like this. Okay, as you increase the number of samples. Okay, and yeah. So and if you increase the number of samples, then you can calculate the mean. Okay, the mu with a standard error of this much. Okay, for a sampling distribution, the error, and as I mentioned earlier, error means the variation. Okay, the variation in the data can be calculated as sigma upon root of n, where sigma is the standard deviation and n is the number of values we have in one sample. Okay, so your mu or your mean will vary as per this much. Okay, and you can apply the central limit theorem to this thing. Okay, so this value, standard error, tells you about the precision of your value. Okay, how precise is your value? obviously, if a standard error is high, that means you have a lot of variation in the data. The precision level is low, and vice versa. Okay, if the standard error is low, then means the precision is very high. And standard error depends upon what? Standard deviation and number of samples. Obviously, standard deviation we cannot control, but the number of samples can be increased and decreased. Okay, so you can see here. Huh? As number increase, this will decrease and it will become more precise. Okay, we need a break. 5. Okay. So if you want to see the central limit theorem in practice, okay. For example, we have a non-normal population. Normally, the distribution of intervals is not normal. For example, if I say distribution of number of beakers, it's normal. Distribution of interval between the beakers, not normal. Getting my point? Okay. Distribution of grades, normal. Distribution of differences between the grades, not normal. This is usually the case. Okay. So let's say we are simulating a non-normal population, which could be waiting times. Okay. Set seed is just a random value from like a starting point. It's random data. Okay. So we have to give it a random seed because it will be non-normal. Normal, we know how to do it, right? Previous example, should normal we know how to do it. This is for not normal. Okay. So this statement will give you a very skewed population. Okay. So this is the rate. Okay. The rate of change. Okay. And 1000 is, I believe, the number of values. Yes. So it will create 1000 samples with a rate of 0.5. Okay. And it is taking basically an exponential distribution. Okay. What's the name for it? Exponential. I think there could be another name for it. The name of the distribution. Last time you were creating random distribution, right? Last example, we created random distribution. Okay, this will create not normal distribution. This will create not normal distribution. Okay, so the distribution which they are using is exponential. Okay, exponential. Exponential is by default skewed. Okay, skewed meaning the mean is not in the center. The peak is not in the center. It's on one side. Okay. Then you can plot the histogram. So this will create the sample, and this will make a histogram of the sample. Okay. So you are creating the sample and storing it in the population. And this is the histogram of the population. And this is the chart pattern. Okay. And then you take 1000 samples, which has n of So now you will take 1000 samples and you will replicate. Oh, sorry, not 1000 samples. You will take 5 samples and replicate it 5 times. Okay. And then you do the same thing. You take 1000 samples. Oh, sorry, you take 30 samples and replicate it 1000 times. Okay. And they are from the same population. Okay. So what we are doing here is we are creating a population. From this population, I will take 1000 sets of 5 values. And then in the next trial, I'm taking 1000 sets of 30 values. Okay. From the same population. And then you plot the two distributions. Okay. This one and that one. Very good. Okay. Side by side. You leave the plot side by side, right? And spread and
I don't know what else to play. It's not basically that's what it's
times 30. This times 30.
much.
This one, right? Is it working for you?
That's what
Sometimes when you copy, if it has multiple lines, then it creates a problem. Yeah, so now you can see the peak. And as we have seen that, or we have said earlier, even if the distribution is not normal, and you take enough samples and enough sets, it starts to look like normal. See, your initial distribution, initial population is exponential distribution. It's not normal distribution. Okay, but when you take 1,000 samples, each of them with 30 values, you start to see a normal distribution, right? So now this normal distribution is not because of the population itself, because of number of samples. Okay, so this is the whole idea behind. Yeah, you can see it's crooked. Okay, and this one is normal. Okay, actually both of them should be like this. So the population is like this. Okay, did it plot the population histogram or no? I mean, it plotted, right? The other one, the previous one. Yeah, this one. See? Actually, both of them should look like this. Okay, but because of central,
exponentially.
the main population from which these samples are taken is this one, the skewed one.
Yeah, but it normalizes that.
It is normalizing.
We increase the population to get this right.
Hmm?
So it will be, if we increase the sample, number of samples, it will be normal. But the population takes time.
Yeah, the
Yeah.
population itself is this. So if you take the whole population somehow, then it will
Yeah.
it's already showing the whole population, right? So now you see the magic of central limit theorem. How does it work? How can it benefit us? Okay. So using the central limit theorem, we can calculate the confidence intervals, which I already mentioned. Okay, the 95%, the 68%, 99.7%. Another, so they give it the name of confidence interval. Okay. The confidence interval for the mean. Okay. So they call it the true mean. The true mean. Okay. By the way, the distribution which you are getting for the samples is for the mean. The graph which you are looking at is for the mean of the samples, those 1,000 samples.
Yeah.
It's not the distribution of the samples, the distribution of the means of the samples. Okay, how many samples you have taken? 1,000. Okay, and each having how many values? 30 values.
Yes.
Okay, and the first case each having 5 values. Okay, so the mean of the distribution of the mean starts to look like normal, not the population itself. Okay, so the true mean is the name given to the mean of the population, the one single value. Okay, so true mean is never like many. True mean is one value. Okay. And you cannot get to the true mean because because you don't calculate the population. Okay. So you can using central limit theorem and using the idea of central limit theorem that the mean starts to look like normal distribution. We can apply it to calculate the 95% confidence level of the mean. Okay, and the mean of the samples or any sample plus minus this. Okay, critical value is what the central limit theorem is giving you for this much percentage. Okay, the empirical rule 68% with 1 standard deviation to 95%, 3 for 9 damage. So that 1, 2, and 3 is a critical value. And then instead of standard deviation, now they are saying take a standard error. Okay, standard error equals to this much. Yeah. Okay. Okay. And yeah. Once you calculate this range, then you will say that we are 95% confident that the mean of the compressive strength will be in this range. Not the compressive strength will be in this range. The mean will be in this range, not the value itself. Okay, the mean. Okay, so if I give you a new sample, okay, and so you cannot say that 95% of the sample will be in this. No. You will say that there are 95% chances that the mean which I will calculate for this sample will be in this. Okay. Okay. And so and still there is a 5% chance that outside the range. Okay. Okay. So this is the code which will calculate the confidence interval, and there are two methods to calculate the confidence interval. The first method is this one, where you are manually calculating the confidence interval. So you do like you do in calculator. Okay, you will calculate the mean. You have the sample. You calculate the mean. You calculate standard deviation. You know the number of samples. You will do x bar and t. 95% of t will be 2. Okay, so you will put in the calculator, right? Mean plus 2 into standard deviation upon root of n. So the first method is this. Okay, this is the first method. Mean plus this into this upon this. The first method. Okay, and the second method is using the t-test. Okay, or basically the t distribution. Okay, so it will also give you the 95% confidence interval. If you want to save the values for method 2, you can put something there and will save the values. You can say like CI and less than and dash before the t-test. So before this line, you can put something to save the value. This value is not saved, right? Okay. If you want to save the value, you can click save it. Anything CI, this and that. Or to save the value in CI. Otherwise, this will only show you. Then working. Mix type, mix name. First, sorry, we have to read the strength data. We did not upload the strength data. It's taken from there. The read command. The one which we had in the previous course. No, before. Sorry. Before the first comment for a single group for this group.
What is comment?
Yeah. Yeah, make it a comment basis. Now Before this, yeah, we do the read command. Where is the file? Is it in the same folder? Okay.
Try with the file name.
File name. Are you still in the same directory? Strength for the risk of complete strength. The second one.
Completed.
Complete strength. You can open it in the file. Okay. If you want to just shift it, do shape and enter. Okay.
Yeah, already.
Go there. You start that. Read. Is it in the same directory?
Should I put it on data set when I press my next one?
Sorry.
It's in the same directory.
Yeah, it should work. Complete strength, maybe that name. Did you use .csql too? No, did you put it with the name?
Should put it on.
I don't. Okay. So, complete the name of the file. Okay. Yes. No. But another one. What is this? A comma, two comma. No, in the middle. And two. Yeah, just type it. What was the other one? Was strings. Strings. False. The top of the level. Do shift shift 10. That's fine.
I have to write it, not CSV.
You have to write do CSV. It works with it. Is it taking the same direction?
So my research and that.
But is it taking it here?
Are you?
You just said it again. Or the session one. Book. Data. Whose data is this? Okay, can you open this file and check? Is it okay, open it? It's yeah, same difference. Maybe the header itself. XA. Yeah.
After the file name, should we write the?
I believe you are writing some notes to yesterday. is up arrow, in the up arrow.
Yeah, we should like this. Yeah, it should be like this.
Legally,
To say that, or just leave the.
the data will store it.
So,
This is for storing. When you store it,
and I'll sit there saying, getting this.
what I will be trying to do, apartment developer, okay, and what can you come down? Especially in the data itself.
And never
So yeah, it's cool. Function. Believe it's using the old version. The old is using the old version. The actual
go, then the plan market.
no, you have to do it with the code.
So, should I go into that library and then,
Yeah.
then the next?
You already put this, right? Is it different?
Store that plan market only needs to be done once. I have it installed.
Yeah, install this solution once.
So, very
Yeah. Just copying this one. That, yeah, this one. Okay, we can, this one. Yeah. And class function. That's the filter.
It's says something clear about hotels. Percentage vision set next time equals to this. How does we test it?
We have a data from function.
Filter has to have the. It's a function of. It goes with the function condition. We have to see why.
Should be equal to x.
I think we have to.
It needs more all arguments.
Yeah, but it needs y equals 9 and then. What is what's wrong?
Okay. So filter, this is the data. Okay. We don't need the percentage. Right? Maybe not. We are doing this, right? Filter. We're doing the first one. Mass will be the numbers. Then they are putting the data there. And then the condition. There is no percentage. Okay. Now, I go on. No, take it from here. Change the name of the data. Take this now.
Is it we just change it to that's
Data, which data is? No, yeah, yeah. No, no. Take all this one. Next time. If there are only good time. Next data equals to data. Yeah, that's fine. Please fine. Fine. Okay. If you keep it data, then like the command. It's like a command. Yes. The command. Data is the command. But from where it came. Spatial. Okay, you go there to the cloud. Take this whole thing. Mix it. Something. How to prepare video name of using the first to the input data frame that you want to do. Data function of a given function. Filter is the main thing, and this is the operator. The data is the frame itself. If we use a concrete string only without CSV as data. Now here filter is fine. Why are we changing here?
Here it was. It's the clear status.
Okay,
So here we use the list.
it doesn't work without it, right? It will try. No, try directly filter.
Again. It's not quite the same. Just
No, no. It work. Then needs to now from here we are taking the next step. Okay, so if we write concrete string here, like it was instead of data, we write concrete string in the filter before the filter.
Yes, it is.
Try without space.
Government.
Without space. No, no, keep it. We're saying it's all. Now try to see as a filter. Yeah.
Actually,
Yeah. Ah, okay. So we have to like put it somewhere. We have to use it with the data command. That is the receiving. Yeah. So we are using what data, right? We have to like one point two.
for the next video. So, I'm checking them. No. In brokerage,
There was nothing. Nothing.
so
Data is the same. Okay, and concrete distance from filter command not one the B. Yeah.
so that's a company.
Yes. So we had to do this data something from good work. Keep it further. Okay. Upper value over here. They had to save the data. But
That's okay, but I mean, take it.
usually you put the whole code. It's better. For PNP is the whole code. The class. It becomes bigger. Okay, so what is giving you the key test? Upper limit and lower limit is same price.
I'm not see this.
See that?
Yeah.
Okay.
I play how it's looking.
No, we save it. If you save it, CI, right? What is CI? No, didn't see it. This one. Please. So if you go without this, run it without this. Without CI. This is the last one. No, keep the field test. It's giving this C and equals to this.
I don't know this.
And this one. Okay. So, again, after so much. Okay. So basically, the first one, you calculate the values like we're doing it on a calculator. The t-test, okay, automatically takes a 95% confidence interval. Okay, and the t-test, whenever you perform it, it will always be performed on 95% of, right? I already mentioned a couple of times, 95% is like from another. So always 90. So you say t-test, the default percentage is 95. Okay, and the same thing in an Excel as well. Perform t-test, you will see. So since it's already used, the purpose of t-test is to check if your required value is possible or not. This is the main purpose of performing the t-test. Okay, and the rule is if your required value is within the confidence interval, we say it is possible. Otherwise, it is not possible. So t-test is by default giving you the interval to check against your value. Okay, this is how it is working. Okay, the purpose of t-test is to check if my required value is within the interval or not. Okay, if it is in the interval, we say the value is achievable. If it is not in the interval, we say value is not achievable. Okay, here because the t-test is working on 95% confidence interval, we are using it to calculate 95% confidence interval. But the main purpose why we call it a t-test is because we are using it to check against a required value. Okay, clear? And the test is checking the required value against 95% confidence interval. Clear? Okay. So if you check the confidence interval, okay, when sample size increases, your standard error will decrease, right? It is sigma upon root of n. So n increases, standard error will decrease. If standard error decreases, your confidence interval will decrease. Meaning not the value, meaning the difference between them. The difference between the upper and the lower value. It will decrease. Okay, right? How much is it now? 38 and 38 and 40. Okay, so if you increase the number of samples, it will be very close to each other. Now it has a difference of 2. Maybe if we increase n, it may have a difference of less than 2, and so on. Okay. If you increase standard deviation, your standard error will increase. That means the confidence interval will be farther from each other. Okay. And if you are going for if you increase the interval size, obviously the values will be far from each other. Okay? This is 90%, this is 95%. So these values will have more interval. Okay. So so you can like check one by one. Okay. So I keep this same, only change the sample size. Then what will be the effect? Confidence interval will become less. If I keep this same, only increase the standard deviation, so the confidence interval will become more. If I keep these two same and only change the range. The confidence interval with more range will become farther and with less range will become nearer. Okay, so you cannot apply it to two data sets where everything is changing, and this is normally the case. Okay, for example, you have two data sets. One has 30 values, other one has 10 values, and both of them have their own standard deviation, right? Okay, so then these rules will not apply because you are at a time changing two things. So maybe because of number of samples is increasing, the confidence interval is getting less, but at the same time, the standard deviation is also increasing. It can compensate with each other. Okay, it can offset the difference. Okay, so for example, if you have unconfined compressive strength for rock as a site. Okay. Rock, there's a rock sample on the soil, the ground is made up of rock, hard rock. You took a sample and you did the compressive strength test. Okay. And you found the confidence interval of 38 and 42. Okay. Or you can change something and you have a confidence interval of 35 to 45. Okay. Which one is better? 38 to 42. Why? Because yeah, the precision is high. Okay. And how can I make it even better? You take more samples, right? And you were saying something? You were saying the research, right? She's senior, if she can see. Right? So you can take more samples, okay? You can do something about the testing machine. So it will decrease the variation in the data itself. So if I recalibrate the machine, if I do the maintenance and everything, okay, so it will give you less error time. Okay, so the confidence interval will, standard deviation will decrease. You can increase the number of samples, or you can decrease the confidence interval. Oh, sorry, the standard deviation. How do you decrease the standard deviation? By doing something with the sampling procedure and the testing procedure. Okay, so the error of it, if the practical error is reduced, the standard deviation will reduce. Okay. Okay, this is the next homework which you will do. Okay, and you have to generate something distributions like we did. You submit the histogram. Okay, and which is not normal. So you can go with the exponential distribution again. So basically, this thing we should do. One data. You are generating your own data. This code is generating your own data. Okay. You can check if you can change this into some other distribution. Okay. This is using exponential distribution. Okay. You can even change the distribution.
So that's exponential.
You can use exponential. You can use some other non-normal distribution. There are lots of them. Okay. And to answer this and this and this. Okay. Let's take a break. Okay. And 10 minutes and come back and see the other part.